Morning. Can people hear me? Hi. Yeah, so let's get started. Just a couple of announcements. So these are almost all the same from last time. The only new one is I will hold office hours directly after class. So normally I answer questions anyway, right outside after the lecture. So let's just make it that the office hours. Yeah. Going forward, it'll be every Wednesday. But you can feel free to, like, people ask me questions on Monday too, so you can feel free to continue doing that. And all the other, this doesn't affect any of the other TA office hours. Those will continue to be held in the room in class. And these are all the same from last time. Homework 2 is due today. The team contract for programming assignment is due by Friday. If you have the same team, and if it worked for you in the first programming assignment, you can just submit the same team contract. And yeah, exam 1, like I said last time, it's next week, so 1 week from today. And it will be on everything up to Monday's lecture, so including prefix sums, but not what we were doing today. Today we're doing communication primitives, but that will not be on the exam. That will just be, you need to know it to do the programming assignment, but it's not going to be on the test. Questions, concerns? Right, so like I said, we are going to switch topics today. We are going to do communication primitives. So communication primitives are mostly distributed memory things. And you can think of them as building blocks for algorithms that involve communication between different processors. So sending data between different processors. And occasionally they can include some small amount of computation. So often there's some communication primitives that are just sending data and some that are sending data plus a little bit of computation, like the primitives that we have been doing so far, like reduction, for example, like you have a lot of numbers, and you want to aggregate them all into one number, or scan, which is another name for prefix sum. That's what we have been doing the past previous lectures. So it's so basic, or it's so like fundamental that MPI actually provides a primitive for that. And this is one example of a primitive. This is broadcast. So broadcast is you have a bunch of processors. One of them has some data in it, and it wants to send that data to all the other processors. So every processor needs a copy of that data, and this is in the end after you commit the broadcast. Okay. And so how do you do broadcast? We talked about this very briefly a previous time, but we can be a bit more precise about it this time. So suppose we have 8 processors and root 0. So every communication primitives usually have one processor called the root, which is like where the data starts. And depending on the communication primitive, data may end up in a different way on the different processors, but the starting point is called the root. And so that's kind of like a hint, because often these things happen in tree-like algorithms. So like that's the root of the tree-like algorithm. So with a broadcast, root 0 has the data in the beginning, and it proceeds in time steps. So the first time step, root 0 can only send to one processor at a time, so it sends to 4. And in the second time step, now these 2 processors, root 0 can send again to 2, and processor 4 can send to 6. And in the one after, then all of them that already had data in the previous step can send to their neighbor one distance away. So 0 sends to 1, 2 sends to 3, 4 sends to 5, 6 sends to 7. And after log n rounds, or after log p rounds, where we have p processors, all the processors will have the data. And the reason that we need this tree-like broadcasting algorithm is because if root 0 were just to send to one processor at a time, like one way to implement broadcast, you could send it to processor 1 and then processor 2 and processor 3 and so on like that. However, that would serialize the communication, because in our model, each processor can only send and receive one unit of data at a time. So that would take p time rather than log p time. And notice that so processor 0 participates in all the rounds, but when you implement broadcast, not all the processors participate in all the rounds. For example, like just look at round 0, only processor 0 is participating in it. In round 2, then processors 0 and 2 and 4 and 6 are participating. So the distance, in some sense, like the distance between the pairs of processor grows the distance between the pairs of processors shrinks with every time. In the beginning, the distance is the maximum, like p over 2, then p over 4, p over 8, and so on, down to distance 1. Here we did from the most significant bit to the least significant bit, but you can do it the other way around as well. And if you have a message size m, broadcast is not limited to sending only one piece of data to all the processors. You can send arbitrary size data in your broadcast, which is parameterized by m. The runtime is tau log p. So tau is the latency constant. Log p is the number of rounds that is happening. Mu is the bandwidth. M is the number of bytes that we're sending, and log p is the number of rounds. So if you factored out the log p, it'd be like log p times tau plus mu m. And one way to see that is there are log p rounds. Each one incurs tau, which is like the upfront cost to start the communication, plus mu m, which is the once you establish the initial contact for the communication, then you send, this is the cost to send m bytes. Questions? So the way to figure out which pairs are happening in each round of communication, we have to be a bit careful. Like I was saying, you can't just naively send from, so like you can, in each round, you can figure out the distance between the processor pairs that are communicating in that round. Like they decrease by half in every round, but you can't just send from all the processors in every single round because not all of them may have the data that they need to send already. And so we need to check if, basically the way it works, starting from the most significant bit, is that the pair is just, you flip the top bit. So 000's neighbor or partner would be 100, which is gotten by flipping the top bit 0 to 1. And you have to check that the lower bits are all 0. And those are how you know the ones, the processors that are participating in that round. And you can just flip the bit with XOR. And to check whether the bits are 0, you can use bit masking. So bit masking, you can do, so suppose that you wanted to do a bit mask with 2. You put 1 in the lower bit, you shift it over by 2, and then you subtract 1. And that would put all 1s in the lower bits. And to check whether the lower bits are 0, you have some number, you AND it with the bit mask, and if the result of your AND is 0, then all the lower bits were 0. So in the next round, so in the first round, we just had 0 paired with 4. In the next round, 0 gets paired with 2, and because 4 now has the data from the previous round, then 4 also has a pairing with 6. And we got their pairs. By now we were at the most significant bit. We switch one over to the right. We flip the bit to get the partner. So here, 000, you flip the middle one, goes to 1010. And here, 100, you flip the middle one, goes to 110. This is just some pseudocode to do it. So if you want to broadcast with root 0, this is how you write, I guess now you're familiar or have some experience writing MPI code, but if you remember, the way that you write MPI is every processor runs runs a copy of the program, and every processor has their own rank. So if you were thinking about how would you implement these primitives with just send and receive, then you need to use your rank, which is the bit string that describes which position you are, to determine who your partner is in every round and whether or not you are communicating in that round. So like this is kind of if you think about like when people were writing MPI, they first started by implementing send and receive functionality. And then like you have to develop the language. It just doesn't come for free with all these primitives that you might be interested in using, like broadcast. So people have to build this base functionality of send and receive, and then implement all these higher level primitives from those. So this is the first step. in each round. So D is the number of bits. This is the this is whether or not you flip it, and then mask is just the bit mask. You do it. So we start from the highest bit and we're going to the lowest bit. So the highest bit is D minus 1. The lowest bit is 0, left to right. And so this is if you are participating in this round, which is my current rank, and the mask is 0. So that is all the lower bits are 0. And so there are two cases. This is if I'm participating in this round. And if I am, there are two cases. One is I'm the sender, and the other one is I'm the receiver. And so the way that you tell whether you're the sender or receiver is you look at your bit, like the bit that is currently under consideration. If it is 0, then you are the sender. If it is 1, you're the receiver. And then in the next, to move on to the next iteration, the mask needs to shift over by 1 because we're moving 1, and the flip bit also needs to shift over by 1. So the flip bit is just 1 in the current position that we're considering, and the mask is 1s in all the lower positions from that. Questions? Okay. There are a couple issues that this code doesn't consider, like, for example, what if the number of the processors isn't a power of 2? And also, what if you're interested in doing broadcasts from a processor that is not 0? I think we have seen this trick before, which is if you don't have a power of 2 processors, you just pretend that you have the next power of 2, and you just have to do check that if the processor that if the logical processor that you're trying to interact with doesn't exist, then you don't send or receive to that one, because you shouldn't send or receive to something that isn't there. And yeah, so this is an example, like if you only had 6 processors, you would cut it off here. But logically, you could run the algorithm for all, like every processor that you actually have would run the code here, and then you would just check if the partner, which is rank XOR flipped, actually exists. And if it doesn't, then you just don't, just continue. Mhm. Yeah. 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 So just looking at this code, you just add an additional if check to see if the processor rank XOR flip is your partner in this round, and if your partner is not actually there, then you would do nothing. So that handles the case if we are broadcasting sort of in a non-power of 2 processors. Yeah, so you just pretend you have the next power of 2 up, you run it as if you have the next power of 2, and you just ignore the other ones that are not there. What if the root is not processor 0? Well, the easiest way is we have an algorithm to do broadcast from processor 0, so you could just send the data to processor 0 and then run the broadcast algorithm from there. That would incur an additional additive factor of tau plus mu m, because there were log p rounds before. Now you just add an additional round from that processor sent to processor 0. That's not bad. Like it doesn't show up in the asymptotics, like in the theta notation. It's just a +1 in the height. But we can theoretically do even better with no additional communication. Mhm. Mhm. Yes, exactly. So the comment was maybe we can do basically some bit manipulation to map any arbitrary root onto processor 0, and then we have to map all the other processors to this logical representation as well. Yeah, that's exactly what we're going to do. Yep. So this is how we can represent the broadcast tree. In starting from root 0, in round 1, 0 sends to 4, round 2, 0 sends to 2, round 3, 0 sends to 1. And then the numbers on the arrows are just the rounds that this communication is happening in. And so we have this broadcast tree, and if we have an arbitrary root, we can make this broadcast tree with any root using bit manipulation. The that needs to hold for this new broadcast tree is that every rank has to show up exactly once in this tree, because in the broadcast, every rank needs to get the data, but it shouldn't send or receive more than, or it can send multiple times, but it shouldn't receive the same data more than once. And we should respect hypercubic permutations because, like we were saying earlier, it is unusual for computers to actually support arbitrary permutations in constant time. And a lot of algorithms lend themselves nicely to hypercubic permutations, which is that you just flip one bit. Sorry, every pair of communicating processors in a hypercubic permutation just flips one bit. So like, could be the top one, could be the lower one. Any of them is fine, but it just has to be one of them. And it turns out that that is a subclass of permutations that actually maps really well to tree-like algorithms. Like, kind of like we're seeing, a lot of these algorithms have the form, you figure out a partner some distance away from you, and in the following rounds you have a new partner, and maybe it's a different partner, but the distance is shortening or growing each time, depending on how it goes. So yeah, so in this example, let's say 0, 1, 1 is the root. And the way that we make the broadcast tree with 0, 1, 1 as the root is to do an XOR with all the elements. So anything XOR with 0 is just itself. That is the root. So we're going to XOR 0, 1, 1 with the root. And in the initial logical broadcast tree, we had 1, 0, 0 as the partner for 0, 0, 0 in the first round. And 1, 0, 0 XOR 0, 1, 1 is 1, 1, 1. So now in this new broadcast tree, this one is going to send to this one. And notice that it only flipped one bit. The top one. And that is maintained because the way that we did the initial broadcast tree is we flipped only one bit from 0, 0, 0 to 1, 0, 0. So the XORs would also follow the same property. So we're going to do the same thing. Just we have this initial logical broadcast tree, and we want to map it into a new one with a root that we're actually interested in. So we do XOR here, 0, 1, 0, XOR with 0, 1, 1 is 0, 0, 1. 1, 1, 0, XOR with 0, 1, 1 is 1, 0, 1. And these are one bit different from their sources. So the difference between this one and this one is that the middle bit got flipped. The difference between this one and this one, also the middle bit was flipped. And the same for round 3. Just we do XOR again with the root rank with all of these. And this will get the properties that we want. So every rank will be represented once in the tree, because in this source tree, every rank was represented once. And so if we XOR them with all the same thing, they will all get something unique that will be uniquely represented in this tree. And also it will respect this property of just one bit flipping in every round because the initial one did as well. Yeah, so this part is called the virtual tree, and this part is called the real tree. And the virtual tree you can just generate like logically through code. And the real tree, once you have the actual root, then you can generate this. And you just go back and forth between them with XOR. So you can just do bit manipulation on the rank. So if we want to change the code to accommodate non-zero roots, we convert the rank into the virtual tree using XOR. So the root is given as something that is not 0. And so this rank is the rank in the true rank, and then we need to convert it into the logical tree. This is just basically the same code as we had previously, but now we just add a little bit of extra XOR. And yeah, so this top line top if is if I'm participating in this round. This inner part is if I am participating in this round, I need to find my partner and I need to figure out whether I'm sending or receiving. And that is these two parts. And then, yeah, and then you do the communication on the real tree. So you have to flip it back. Otherwise, this is the same.
So over here, what do we do with number of processes, not a power of two? For example, in the example, first 1, 1, 1.
Yeah, good question. In this case, if you have a non-power of two processor, you can do the same thing, but you just need to do it on the real rings, not on the logical rings. So like if you think back to the original code, the original code is just the same as this, except without these XORs to map us between the virtual and the real tree. And so the way that we ignored the non-real ones there, where like we would just add an if check to see like if the rank that I'm interested in currently does not exist, then just do nothing. Or yeah, if the rank that I'm about to send or receive does not exist, then don't do it. And so here we would just check if the current rank does not actually exist. Good question. Other questions? Okay. Yeah, so this is just a simplified version because when we actually do this out, we have some repeated XOR. So we just can cancel those out. And this again respects hypercubic communication because you just flip one bit in each round. Questions on that part? So that is the end of broadcast. And yeah, so you can do similar algorithms. So like this is kind of the structure of a lot of these primitives, which is you do a tree like kind of reduction. Broadcast is like the opposite of reduction in some sense, because broadcast is like you have one thing and it wants to go to all of the things. Reduction would be like everybody has one thing and you need to aggregate it onto one single processor. So you could implement reduce as just kind of like the inverse of broadcast. Rather than running from the top down, you would run it bottom up in a tree-like fashion. There's a variant of all reduce, a variant of reduce called all reduce, which is, so normally in reduce, everybody has some data and you need to aggregate it onto one processor. In all reduce, all the ranks should get all the results. So this is similar to when we were doing the scan. We were doing like the prefix sum and we were calculating the total sum for everyone. And that's kind of like an all reduce. So every processor gets the total sum. And the algorithm to do that is similar to what we're doing in scan, which is you use the entire hypercube. Yeah, and then there's also scan, which is sums. All of these have the same complexity as broadcast. So tau log p plus mu m log p. This is not on the exam on Wednesday. And also in future exams, when this will come up, I will give like a sheet with all these bounds, so you don't have to memorize this. The questions are, the more interesting questions are like, how do you use the primitives to implement algorithms rather than like try to memorize the runtime for the primitives? Because if you build the algorithm using primitives, then you just add up the times for the primitives. Yeah, so this is reduce, which is, you have 8 processors in this example. Every processor has some data that they need to aggregate. And let's say they're trying to aggregate it onto processor 0. So the right half, in each round, the right half sends the data to the left half, and they can aggregate it. And the total world cuts in half each time. So first round, everything is there. The right half here sends their data to here, and they add them up. Yes.
I remember seeing something like math. I remember thinking, our MPI called scatter and gather. Are those primitives as well?
Yes, we're going to get to those shortly. Yeah, the question was like, what about something like scatter and gather? And we will do those also today. Yeah. So those are maybe a little bit harder to implement than broadcast reduce. So we're going to do simpler ones first. So reduce is like this. You send your right half to your left half. You cut the world in half. You send the right half here. to here, and then you keep repeating this process. And the reason that you can do this is that in this round, now after the aggregation, this node would have this plus this. And in the end, they would all end up on processor 0. And all reduce is similar, except this is kind of similar to the scan algorithm that we had before, where you compute the total sum on every processor. You use the entire hypercube to compute the all reduce. All reduce, again, is every processor has some data, and you want to add it all up on all the processors. So every processor would have the total sum in the end. The runtime is the same as for broadcast. Right? Oh, okay. Never mind. I thought you had a question. And the reason that the runtime is the same is because the number of rounds is the same, and the parallel communication in every round is the same. It's m bytes, and the startup cost is tau. So it doesn't cost extra to use more parts of the hypercube in this model. Just counts how many rounds you're doing and how many bytes and how many kind of new connections you have to do in the different rounds. Okay. Now we'll do gather. So gather is kind of like reduce, but you're not aggregating them with an operator. So with reduce, if you have p processors and each one has one piece of data, then in the end, processor 0 would have one piece of data. But in gather, if p processors have one piece of data each, in the end, processor 0, or whatever the root is, will have p pieces of data. This is the picture. So this is processors, this is data, and with gather, every processor has some data, and in the end, the root processor will have all that data. The data should be ordered by source processor in the end after the gather is done. And when you run the algorithm, from the practical perspective, when you run the gather, it should be much less than the actual problem size, because otherwise the algorithm will just be worse than serial processing. Because remember that any processor can only receive one unit of data at a time. And so if you're sending the entire data to one processor, then that would just serialize the computation. But a common pattern is not to send all the data, but every processor does something, and it makes maybe it does a reduction, for example, or it collapses the data into something smaller, and then you gather that data to do something. All gather is another primitive that is similar to gather, except that every processor will get the entire answer. So the relationship between gather and all gather is the same as the relationship between reduce and all reduce. Just in gather, only the root rank would have all this data. In all gather, all of the ranks would have all the data. And it should be ordered in terms of source. So the way that we implement gather is similar in terms of communication to the way that we can implement reduce, because they do feel very related. The goal is to get all of the data on one processor, but it's just a question of whether we're collapsing it down or not with an operator. So with gather, we use the exact same communication lines that we did as with reduce, but now the data doesn't get smaller as you do the gather. So the data actually grows, or sorry, not smaller. The data grows as you go through the rounds, rather than like in reduce, the data stayed at a fixed size because in each round everybody got one piece of data and then you aggregated those. So 2 becomes 1. But here there's an aggregation, so the data size that is being sent grows exponentially in every round. The number of rounds is still log. And we have a similar thing for all gather. Again, the communication is the same as for all reduce by using the entire hypercube, but the difference is that the data grows exponentially in every round because, so in the first round, everybody has M data and sends it to somebody. And now in the second round, everybody has 2M data and needs to send all that data to its next partner. Yeah, we will get right there. Good question. Yeah, so you do have to make sure the data is in order at the end. That's the meaning of gather and all gather. It was easier when we had one root, like with gather, because you know where everything is coming from. And here you also do know where everything is coming from. So it's easy for gather, but it's slightly more complicated for all gather, which I will get to in a moment. Other questions? Okay. So yeah, so like you just said, it's a bit hard to get them in order. One way to do it, like the easiest way to do it, is everybody allocates, let's say m equals to 1. The easiest way to do it, you allocate an array of size p, and you know the source processor that everything is coming from, so you directly put it into your buffer of size p. Like you can directly index into that. Ideally, we also like to make the data access contiguous, which that doesn't allow us to do because we're directly indexing arbitrarily into some array. So yeah, we can do something slightly fancier. But just to illustrate the issue is why we need to go a little bit further. So even in this first round, 0 is setting to 4. And like in this communication, we know that we are 4 and 0 is setting to us. So we could just index 0 into our output array and put the data there. But that is random access into this array. Does the problem make sense? So to do something slightly fancier, we want to do an in-place altogether. This is the initial start of your data. We have 16 processors, and this is the data this way, and everybody has one piece of data, and we want to all gather it onto all the processors. So in the end, every processor should have 0 through 16 like this in this array. And the way we do that is similar, like we do these pairing of processors. So here we start with the least significant bit, and the pairs are just neighbors with the least significant bit. And the reason that we are starting from the least significant bit is because we want to do contiguous memory indexing. And if we set our neighbor to the just one bit away from us in the lowest bit, then you're guaranteed that the position is right next to where our current data is. Like, for example, 0 and 1. 1 is right next to 0. The pair is here. 2 and 3. 3 is right next to 2. So that is the first round. And so we had pairs, which are just the two right next to each other. In the next round, the pairs become distance 2 away from each other. So like 0 gets paired with 2, 1 gets paired with 3, 4 gets paired with 6, 5 gets paired with 7. And that is from hypercubic permutations. So now we flip the second to lowest bit, second to least significant bit. And we have this, again, this contiguous property. So now 0 and 1. After the first round, they both have 0 and 1. And 2 and 3, after the first round, they both have the data 2 and 3. Now they do this exchange. And notice that 2 and 3 are contiguous with 0 and 1. So we're going to do this exchange, 0, 2, 1, 3, and so on for the rest of them. So yeah, so after that, then the first 4 processors, 0, 1, 2, 3, 4, all have the first 4 pieces of data. The next 4 processors all have the next 4 pieces of data. So you can think of this, you kind of like put them in groups. And if you think about it recursively, like each one of the subproblems should do this in-place altogether for each of the subgroups. So it extends to this. Each group of 4 processors will have a contiguous chunk of 4 pieces of data. So the next one we do the similar thing. Now we just pair things that are distance 4 away from each other. and they do this exchange. Now, the first half of the processors have the first half of the data, and the second half of the processors have the second half of data. And that data is all contiguous. And finally, the last pair is distance 8 from each other. So the thing to notice in the all gather, which is similar to the gather, is that the data is growing at every time. Like in the beginning, everybody was exchanging just one piece of data. The next round, everybody is exchanging 2, then 4, then 8, and so on. This is the last one, this is 8. And then in the end, you do this exchange, and everybody has all the data. And all the pairs of processors that are exchanging in every round are distinct. So like there's no overlap in the permutation. 0 is paired with 8, 1 is paired with 9, and so on. And so all those exchanges can happen in parallel. Yes. Question. So yeah, let's just look at this one, like P0 and P8. P0 is sending the first half of data and receiving the second half of data. And vice versa, P8 is sending the second half and receiving the first half. So in every pairing, you're both sending and receiving, and the amount grows in the different rounds. And that is the end. Yes. Yes, the message size is growing in every round. So if you remember, like in the beginning, everybody started with 1. And in the first round, they each send and receive 1 piece of data. But in the second round, everybody has to send and receive 2 pieces. Like processor 0 sends these 2 and receives these 2. So the message size is exponentially increasing in every round. 1, 2, then 4, then 8, and so on. So yeah, so that's why you want to do gather and all gather on data much smaller than the problem size, because if you are doing this, if you're doing this full exchange of the entire problem, then or if the full exchange of the entire input size, then it would take a long time. Other questions on this part? So to calculate the runtime, let's say that everybody has a message size m in the beginning. So in the example, it's just m equals to 1, but you could have more pieces of data in the beginning. And the way that we do this is we have log p rounds. Each one takes tau plus mu times m times 2 to the I, where I is the round. So starting from I equals 0. So in the first round, 2 to the I is 1. 1 times this thing is just mu m. So in the first round, everybody exchanges m data. In the next round, everybody exchanges 2 pieces of data, then 4, then 8, and so on. And if we expand this out, then this is just tau log p. And this is mu times m times the summation, 1 plus 2 plus 4 plus up to p over 2. And if you resolve this, this is just p, basically. Oh, tau is the latency constant. So like when you first start to send to a new processor that you haven't sent before in a previous round, you have to incur tau again. That's like the cost of startup sending some data. Once you have established the connection, then the data sending is governed by mu, which is the bandwidth. So like tau is like the cost of startup sending, and then then mu is like once you start sending data, that's how much it costs you per byte to send. So in the end, we get tau log p because there are log p rounds, and each one, the pairs are different. So that's why we have to incur tau each time. And then plus mu mp, because this used to be mu m log p in reduction and broadcast, but it is mu mp in the case of all gather and gather because the data doesn't get smaller. Okay, I'm good. Yep. So the inverse of gather is scatter. And so scatter is you want to distribute the data from some root and partition it across the processors. So that's different from broadcast, because in broadcast, everybody gets the same data. Like in this picture, root 0 has red, and everybody gets red. But in scatter, root 0 has some array that needs to go to all the different processors, partitioned up by the processor. And so 0 gets red, 1 gets green, 2 gets dark blue, 3 gets light blue, this picture. And so the input to scatter is an array rather than, in broadcast, it could also be an array, but if the input to broadcast is an array, then everybody would get the entire array. Whereas in scatter, if the input is an array of size p, for example, everybody would just get one element. And similar to gather, the message size should ideally be much less than the input size for overall speed up, because otherwise this thing is bottlenecked by sending. And the way to implement scatter is basically like it's sort of like broadcast. So, but rather than send, so in broadcast, processor 0 sent the entire data to processor 4. In scatter, processor 0 just sends the second half of the data to processor 4. Because kind of similar in broadcast, like the processors that get data become helpers in the next rounds. And so if you send the second half of the data here, then it again can send away its second half to this second half. And then similar for this left part, then processor 0 now has only the first half of the data because it sent away the second half. And so it sends away its second half of the remaining data, which is like the second quarter, and so on until the end. So the data is dropping off exponentially rather than growing exponentially with gather. So if each message size was m, we have p processors. In the first round, we send m times p over 2, because that's half the data. The total data is m times p, because there's p processors, and each one will get m by. The second round is m times p over 4. Third round is m times p over 8. And this has runtime, if we do the analysis, is equal to gather, because it's the same summation that we just had, but in reverse. Questions? Okay. So these are the runtime summaries of what we have talked about so far. Broadcast, reduce, all reduce, and scan have runtime tau log p plus mu m log p. Gather, all gather, and scatter, they have tau log p plus mu mp. So the difference between these, tau log p is the same. The only difference is the second term. This one has a log p, this one has a p. And when you run your algorithms, in general, of course, we should try to use the primitive with the smallest runtime. So like if you could use a reduce or if you could use a reducer and all reduce, then you shouldn't use a gather or all gather. And vice versa, like if you can use a broadcast and it would still work, better than using a scatter. And the last one that I want to do is all-to-all. So all-to-all is more like a transpose. So if we have 4 processors, and these are the processors, and this is the data. So processor A has data A0, A1, A2, A3. Processor B has data B0, B1, B2, B3, something like that. Then after an all-to-all, processor A will have A0, B0, C0, D0. So this is the first element on each processor before the all-to-all. And after the all-to-all, processor 0 will have that first element, all the first elements. And similar for the other ones, after the all-to-all, processor 2, this one, will have the second element, this column. Like when would we use all-to-all? So in algorithms, actually all-to-all comes up a lot sometimes, because one example that you could think of, that I can think of, is like if you want to do an index exchange. Like every processor has some array that it needs to index into, and each one of those processors, so like every processor has an array, and some part of that array needs to go to every other processor. And first you do an exchange of the indices, which is how much data is going to every processor, and then using that exchange of indices, then you do a final round of communication to do the actual data. Does that make sense? Yeah. So like you could, similar to scatter and gather and stuff, you should not use it to scatter, or you should not use it to move all the data. You should just use it to move small things. So like indices would be much smaller than the actual data. Yeah. Mm-hmm. Yes, the received data should also be in order. Good question. So this is another way to visualize it. It's just like a matrix. So M sub ij is a message from P sub I to P sub j. And so M00 is just staying here. M01 is a message from 0 to 1. M02 is a message from 0 to 2. So on. In the end, yeah, like this one, for example, M21 from 0, or from 2 to 1. And then here, after the all-to-all, you can see indeed, on processor 1, we got this message from 2 to 1. So there are a couple of ways that we can implement all-to-all. The simplest way is just send the data directly. So we have for all P sub I, for j 0 up to P minus 1, we just send the message directly. P sub I sends to P sub j. Is that good? Huh? Why? It takes P rounds for everyone. One potential concern is, like, if you remember in our model, every processor can only send or receive one byte at a time in each time step. So one issue is that the for loop, everybody sends to processor 0 at the beginning, then everybody sends to processor 1, and so on. It's a problem. But we can resolve it, like you just offset a little bit. So in the initial formulation, this is not ideal because of the issue that I just said, which is that everybody is sending to the same processor at the same time. So like everybody is running this code, and everybody sends MI0 to 0 in the beginning. So the runtime is proportional to P squared rather than something like P, because in every round, there are P rounds, and in every P round, you have to queue P sends and receives. So this is not good because it serializes the communication. But this can be easily fixed, which is that you just offset who is getting sent to. You can still run the for loop over j from I to P minus 1, but you just offset the destination for everyone. So rather, previously this was everybody sends Mij, everybody can send M I plus j. So this is offsetting the destination processor by yourself, by your own index. And then we just need to do mod b to make sure this comes around to the correct range of processors. And so that reduces it to something proportional to p rather than p squared, because using this, everybody is sending to a different processor. In one round, everybody sends to a different processor. So there's no need to queue up receive. One thing to notice, which I guess makes sense in this algorithm, is this is proportional to p rather than log p. So in the previous algorithms like broadcast and gather and scatter, those are like tree-like algorithms. And we had p processors, and the number of rounds was log p. So that was proportional to tau log p. But now we have this tau p because we send directly to p different processors. And this algorithm assumes that you have arbitrary permutations, so you can route arbitrary sends and receives. If you cannot, it becomes more complicated. So if you have hypercubic permutations only, you can implement all-to-all using a similar communication pattern, similar to like all-gather. And it actually is a little bit, so in all-to-all, the data stays constant through the entire thing. It's neither decreasing nor increasing, like gather and scatter. But unfortunately, this data is large. So the total size of the data is n times p. This is the total size over every one. And only half of it gets sent at each time. So there are log rounds, and in each one, this is np over 2. And the way to implement that, so this is using, just looking at one example of p sub 0. So in the beginning, p0, you have the 8 processors, has some message destined for each of the 8 processors. So like this one is going to 0, this one's going to 1, going to 2, up to going to 7. And in the end, remember that we want all the data to be ordered in terms of the. So here, the data is ordered in terms of the destination processor. And later on, we're going to order the data received in terms of the source processor. And the way to do it with hypercubic permutation is that we send away, in each round, we send away the second half of the data. And then we do some interleaving once we receive data. So the first round, there's only sending. Well, I guess you could think of it like you send this first half of data, and then you receive, or sorry, you send away the second half of data, and then you receive the first half of data from your right partner. So like 0 is partnered with 4 in this one. And if you're in the left half, you send away your second half. If you're in the right half, you send away your first half. So this is why we got 4-0, 4-1, 4-2, 4-3, because processor 4 sent away its first half to us. And so we have left 0, 0, 0, 1, 0, 2, 0, 3 on P0, and we got 4, 0, 4, 1, 4, 2, 4, 3. And we shuffle them in, so like you just put them interleaved like that. And we keep repeating this process. So in the next round, the partner is with 2. And so we receive the left half from processor 2. 2, 0, 6, 0, 2, 1, 6, 1. And the reason that we have 6 here, so this is not only 2, even though our partner is 2, is because in the first round, 2's partner was 6. And they participated in the same exchange. And so we receive the left half, and we do the blue is send, and red is receive. So we send away, we always send away the second half. You receive the same amount of data, and we interleave it into into our array. And then finally, after log rounds, this is all the data that we wanted. So 0, 0, 1, 0, 2, 0, 3, 0, up to 7, 0. The second thing is the destination processor, and we are processor 0, so we wanted to get all the data with 0 in the second index. The runtime is, so there are log p rounds. So this is tau log p, but the message size is large. This is mu mp in every round, and there are log p rounds. So the runtime is different from this arbitrary thing that we just, so the arbitrary thing is much easier, like you just send. But if you don't have arbitrary communication, then you have to use something like this for the hypercube. And there are some settings of M and P where this is better than the other thing, but it depends on your message size. To summarize the runtimes, we had all of these before. The new ones are these all-to-all runtimes. So for arbitrary permutation, there are p rounds. Each one takes tau plus mu m. In hypercube, there are log p rounds, but each one sends mu m p data. It's not necessarily better because, like, this thing is smaller than this thing. Like, mu mp is smaller than mu mp log p, but tau p is larger than tau log p. So it depends on the relationship between these. And like, there are some settings of p where like this is bigger, where this will dominate, and some settings of p will, or some settings of like m and p where this will dominate. It is for sure easier to implement the arbitrary one, like send. But, if like a programming language for some reason it doesn't support arbitrary send, then you can implement the hypercubic one. Okay. I think this is the last thing in this topic, but the last thing is many-to-many. I think this is what you have to implement in your homework. So if you have, please let me know. Many-to-many is a generalized version of all-to-all. So in all-to-all, everybody had a fixed size data that they needed to send to everybody else. And like in this matrix previously, everybody has some data that needs to go to every other process, but these were fixed size in all-to-all. In many-to-many, they can be different sizes, which makes sense because they probably will be different sizes. Like you probably don't want to send the same fixed size data to yourself as you do to other processors because you already have it. So you don't need to participate in this exchange. Processors can have variable data that they need to send to other processors. It can be 0. And we use the same notation here. M sub ij is the message from P sub I to P sub j. And now we introduce this new thing, which is like just the size. So these bars mean the size in bytes. If you sum up, if you take the max over the rows and you sum up over j, that's the maximum number of bytes you need to send from any given process. So if you sum up each row, that's how many bytes each one needs to send. And if you take the max over those, that's the max that any one processor needs to send. Similarly, if you take the max over the columns and you sum up the rows, that's the maximum that anybody needs to receive. So if you sum up this way, you sum this up, this is the maximum that this is how much processor 0 is going to receive. And this is how much processor 1 is going to receive. So if you take the max over the columns, that's how much anybody is going to receive. Okay. So for many-to-many, you can implement it using all-to-all, and I will show you how. So in initial setup, we have some variable message size that's in for every processor. And for example, let's say we have 4 processors. This is processor 2. to processor 2 has this amount of data that it needs to send to processor 0, has less than it needs to send to 1, about the same, similar, that it needs to send to 3, and none that it needs to send to itself. So like there's no M22. And the way we can do it is basically we want to make the data sending uniform. So we have all-to-all, which is if each message size was fixed size, then we would know where we could just feed it into an all-to-all. And so we're just going to cut it up to make the data sizes that we want to send uniform. The first step is that you cut up every outgoing message into evenly sized pieces. So we had M20, M21, M23, and we cut M20 into 4 even pieces. We cut M21 into 4 even pieces, and we cut M23 into 4 even pieces. So these P0 chunks may not be the same size as each other. Like M21 is smaller than M20. And so its respective piece of P0 is going to be smaller than this piece of P0. But nevertheless, we can cut them up like that. And then we aggregate them into P0. And now that makes the communication size uniform because each processor, so these 3 P0 pieces are going to go to P0. These 3 P1 pieces are going to P1. And that is making the communication size uniform, and that is an all-to-all with max message size S over P. Remember that S is the maximum bytes that any one processor needs to send. In the second step, okay, so this is clearly not finished because now processor 0 has some random stuff like destined for processor 1, destined for processor 3. But we can do it in a second all-to-all. So now processor 0 has some stuff that is not destined for itself, but it needs to send that away. And it can do that with an all. But the insight is that you can send it away with an all-to-all. Like it has some stuff. Here now processor 0 has a piece for itself. And processor 1 also has this piece for itself. But in the end, this processor 1 piece needs to end up on P0. And we're going to do that with a second all-to-all. And similar, like processor 2 has this piece that needs to end up on P0, so on. Yeah. So we just do a second all-to-all where we route the messages in the correct way. And that is in a second all-to-all with max message size bounded above by R over P, where R is the maximum received data that any processor needs to get. Maybe this is also answering your question, why would you ever need to use this? You can use it for many-to-many as well, which is a more common thing. It's just more general. So we have this runtime previously for all-to-all. This is tau times p plus mu mp. That's the arbitrary time. And stage 1, we have maximum message size S over P. So we just plug it in for M. In stage 2, we have message size maximum R over P. So we plug that in for M in the second part. And you add them up. So the total runtime is tau times P plus mu quantity R plus S. Questions? Okay. So one tiny issue that we need to fix is we have to assemble these fragments at the beginning, but we need to know the size of each box because like these are just bytes. So if you concatenate into this segment, the section is going to P0. but it has parts that will end up not on P0, like, for example, this part and this part. So we need to somehow put some special character or boundary to indicate where they change over. So we need to add slightly more data, like plus P. And so that just slightly changes the runtime. Rather than S over P, it becomes S over P plus P, because we need P boundary elements. So we do the same for both. In stage 1, stage 2. And the total is just what it was originally, but with this plus P squared. And if this P squared is a small order term, then we would just get the original runtime. I think this is probably the last slide, but yeah. So any questions on this part? So this is important to know because this is what you should probably, this is what you'll implement in the programming assignment. Yeah, so let's go back. So yeah, so this is just where we started, which is we want to send arbitrary sized messages to the different processors. So this is just a relaxed version of all-to-all. Yeah. These are all going to go to, so this chunk is going to go to processor 0, this chunk is going to go to processor 1, this chunk is going to go to processor 3. Yeah, so basically the high-level goal is that we want to convert this non-uniform data sizes into uniform message sizes. And the way that we do that is by cutting up so we have these messages destined for all the different processors. And we cut them up uniformly into P pieces. And so if you add them, so like message design, the message going to 0 is getting cut into 4 because there's 4 processors. Message going to 1 is getting cut into 4, and that's 4 processors. And if you add up, and the goal of this is that if you chunks like P0 and P1 and P2, those are all going to be the same size. Because like the parts that are going to P0 are like this plus this plus this. And that is the same size as this plus that. Because we cut them all up evenly. Yeah, so this is not finished. So we set up an all-to-all with this as the data going to the different processors. And so the good thing about that is we can, because suppose that we only have an all-to-all function that lets us send evenly sized data to everyone. But this is not finished because like this entire thing needs to end up on processor 0. But like in the initial exchange, this stuff is ending up on processor 0, and this stuff is ending up on processor 1. So it's not done because like now the rest of it needs to show up on processor 0. And the way that we do that is through a second exchange, because now processor 0 has this data, processor 1 has this data, processor 2 has this data, and processor 3 has this data. And these are all evenly sized. And so we can put that into an all-to-all. So like, remember, all-to-all is like this. That basically we're splitting this thing up, for example, to be like the data here on the different processes. And then you do an exchange like in the rows. Yes, exactly. Because suppose that we only had like something that can do even like fixed size blocks, fixed size even blocks. But ideally we would want to do something that can do arbitrary size blocks for everyone. And so this is just converting the arbitrary size blocks into the same problem with even size.
So the size of the set is uniform in a single processor, but across processors, they might be a different.
So here, they're in this first exchange, these are the same size for every process. Like their size going to processor 0 is this plus this plus this. And the size going to processor 1 is this plus this plus this.
So these are all messages that are sent by people.
Uh-huh.
So if the messages that were sent by people might not be the messages
I think that's where this max comes from. So the max size that anybody is going to send is S. And so the max, so let's say that like some other P, like P5 or something, has this max S. The maximum, the chunk size that I would have to send in all-to-all is S over P. And so I guess that everybody else does padding or something.
In both cases, we're just trying to count the maximum size.
Yeah. Good question. Yeah, because it's right that like not everybody, like if you add all of these messages up, it's not going to be the same across the different processors. But we parameterize that with S. And so we run the all-to-all with this size S over P. But not every process will have S over P data to send to every other process. And there we just use padding. And that's why we need like the boundaries. Yes, yeah. So at the end of the first stage, P0 has this piece, which is some of the data that is going to end up on P0, some of the data that will end up on P1, some of the data that will end up on P3. Yes. Some of the data for everyone will end up on everyone. And so that's the reason that we need to do the second round, because that is exactly what an all-to-all is. Like we need to do this. What happens after the first round of all-to-all is that we have things set up in this format where like if the columns are the processors, then everyone has some data destined for everyone else. And that's exactly what we need to do in this exchange. I think that is it. So this is just exactly the same runtimes as before, but now with many-to-many bounded by RNS, which is the maximum number of bytes received and the maximum number of bytes sent. Yeah, and that's the end of time. Thank you.